Well, we have the same exact routers, but this time what we're going to do is we're going to say router OSPF. Hey, no real big surprise. But we've got one other thing to do here. We've got to define a process ID. And this is just a number. It's specific to this particular router, so it doesn't have to be tied to anything else. Since we're talking about router 2, we can use the process 2. That'll help us remember it. All right, well, what do we got here? Well, the same thing. We don't have a whole lot of information here, but we are going to do a couple of things. Let's actually, oops. This time we're just trying to get a very simple OSPF topology up and running. All right, so the first thing that I'm going to do is the exact same thing that I did before. We're going to do the network, and what are we going to do? We're going to do 192.168.1.0 since we're on router 2, but we've got a couple of other things to do here with OSPF. OSPF uses wildcard masks instead of net masks, and so for right now, we'll just say that wildcard masks are sometimes called the inverse of net masks. Now, wildcard masks are more flexible than net masks, but for right now, we're just going to flop the ones and zeros. So there we are. Now, we're not quite done yet with an OSPF. OSPF has an additional idea called an area. And what I'm going to do in this particular case is I'm going to specify area 0. Area 0 is special for OSPF. It's called a backbone area. And you can build an entire OSPF topology in one area. Now, we'll define area here in a second. But as I'm editing the command here, there's two ways to put this in. I could just put in a number, or I could put in the dotted decimal notation. So I could do this for area 0, or I could do that. All right. So we'll be very specific. And I am going to also do network 2. All right, now if we do the simulation again, we'll see the same sort of thing happening. Router 2, well, we still got RIP going on, but router 2 is spitting out OSPF messages, right? And router 3 is not at this point. So router 2 hasn't learned anything because there are no other OSPF neighbors. Neighbor is a keyword and tricky phrase out there. Let's take a look at one other thing as long as we're here. All right, if we take a look at these RIP messages, we can see a particular set of addresses. Now the source address will be unicast. That's true always. RIP version 1 was a broadcast sort of protocol. This one here, RIP version 2, uses this particular multicast address in the destination, and so that's important. RIP is also encapsulated in UDP, so it goes RIP. Now the funny thing is it says RIP version 1 here, but it's really version 2. So we got the RIP messaging here, we have UDP, we have IP, and then we've got Ethernet. And we've got a special multicast frame. Okay, here's a fun little error in Packet Tracer 2. We have a little spelling error here. And OSPF has a little bit different encapsulation. So we take a look here. OSPF uses some broadcast, some multicast, and in addition, we have the OSPF message here, encapsulated directly into IP. And so we can see not only we have a different encapsulation, but a different IP address popped out there. And I'll show you the other multicast address. Multicast addresses often indicate a particular protocol or a particular set of devices that you want to communicate with. Unless you're doing RIP, you won't listen to 224.0.0.9. Well, let's finish our configuration. And we will do router OSPF. Now I said that the process is specific to a particular router, so we're just going to use 3 here. And we'll do network In this case, we're going to advertise the 2 and the 3 net. Remember, we have the wildcard masks. And then we're going to do area 0. And we'll do, I hope I did both networks on the other router. Okay, so we can see that we got things queued up because our simulation is still running somewhere. There we go. And we'll move it over here. And we can see the 2 routers are now both sending out information, same with the other topology. So they are for each other. Yay, we found each other. Now if we take a look at the messaging a little bit later on, we can see here, maybe you caught it as I was doing this, 224.0.0.5. So these are the 2 routers that have found each other, first of all, and second of all, now we're going to exchange OSPF messages. And this one happens to be a type 1. We'll do the types in another video. But there we are. We still have OSPF directly encapsulated into IP, and we've got now a multicast address that is specific to OSPF. Now I suppose we can take a look at one other thing as long as we're here, because it was one of the commands that you may have seen right here, router ID. Router ID. All right, so we know that this came from this particular IP address, but many times we want to identify a router by a particular ID. Now by default, the routers select a particular ID. Well, what if we wanted to change that? Oh, let's do something else first though. There we go. I'm just checking to make sure I did both networks. So now let's take a look at our routing table. And here we've got our OSPF learned routes. So we've got the O for OSPF, and then again we've got this entry that says here's the destination network and the mask. Take a look at the admin distance though. Now it's 110 and the metric is 2. We're not really sure what that 2 means because clearly it's the same topology, so the number of hops didn't change. So what is this 2 all about? Well, it turns out that it's not only including the hop count but also the speed of these links. Where did we learn this from? And then how long we've known it and what interface did we pick it up from. So this interface in the middle here is F0/1. All right, so they've both learned how to get to the other networks. Let's verify that our topology works. And we'll wait for the ARPS to update again. There we go. All right, so everything works. Huzzah. So there we have it. 2 really, really simple topologies. One is running RIP, one is running OSPF. Now, this is where these 2 protocols sort of diverge significantly. One of the problems with RIP is that it's for small number of networks. And for RIP, infinity, or the unreachable distance, is 16. So we need less than 16 hops over here. But OSPF does not have the same problem. So OSPF can be used on larger collections of networks. Now OSPF also has one other idea here, and well, OSPF has a lot of other ideas. So what you saw here is that I put everybody, all of these networks, into one area. All of these are in one area, and that area was area 0, also known as the backbone area. So what is an area? Well, if we read right from the RFC, OSPF allows collections of contiguous networks and hosts to be grouped together. Such a group, together with the routers having interfaces to any one of the included networks, is called an area. Each area runs a separate copy of the basic link state routing algorithm, and each area has its own link state database. All right, we will talk more about the link state database, but essentially the link state database possessed by each router is its understanding of the area's topology. So all of these routers here exist in a particular area together. So they're all communicating with each other. In this case, we're only talking about two routers, so who cares? But what we could do is expand this topology to many, many networks. Now we'll do one other thing before we call it a day here and talk about that router ID. Now it's useful to have a router ID to not only identify the router that information came from, but a lot of times we want to specify what the router ID is rather than let the router figure it out. So if we look at our simulation again, and we pick up the OSPF messages. All right, so here's one from router 3. And router 3 picked as its ID 3.254. Okay? And if we keep our messages going, we'll take a look here. So the significance of the router ID is that all of the messages that are OSPF are identified as coming from this particular router, but the router picked it. And it might have been the first interface up, it might be the lowest numbered interface. So we'll keep going here. So here's one from router number 2. And router number 2 picked 2.253. But in a more complex topology, right, it might get a little confusing as to which router we're talking about when we see messages. It also is helpful to specify so that you know exactly what's happening when you see information. Also, when we look at things like the output from commands, and we do things like this, we take a look at stuff about the topology that this router knows, and we might say, what's our neighbor out there? Right? So we've got this neighbor ID. Well, what if I had several routers out here and then I sort of have to remember the topology? I don't know. So there are lots and lots of reasons why we might specify a router ID. And so one of the ways that we do that is with a loopback interface. So what I'm going to do is introduce to you the idea of a loopback interface. So the shorthand is L0 or L whatever your number is. But we're going to do the longhand so that everybody can see what it is. And I am simply going to specify a 10-net address. So I'm going to say IP address 10.0.0. Let's see, this one is the 3-net, or the router 3, so we'll do that like that. Okay. And let's do the same thing on router 2. Int L0, and this one will be 10.0.0.2. Okay. Now, what does that look like in my configuration? It's just another interface. Now, it's a logical interface. It's not tied to any particular physical interface. So another reason to get away from router IDs based on IP addresses is that it divorces the idea from a physical interface. So anybody looking at it would not know the ID of the router that it came from. And loopback interfaces are handy because we can manage devices using a loopback interface and not worry about whether or not the physical interfaces are up. As long as we can connect to the router from any way, we can use a loopback interface. Now this is similar to VLAN 1 on a switch or BVI 1 on access points and so on and so forth. Now, if I had had those loopback interfaces up and running when I had built my topology, maybe the routers would have selected those for their router IDs, but let's do this. We're going to say router OSPF, whoops, and this is router 3. So again, handy naming and numbering conventions make it really easy to remember what you were doing. And so we're going to say router ID, and I want to use this. Okay? Okay. Now, what this is saying is that you said this, but I already have a process that I'm using to establish what the router IDs were. So what I'm going to do is do the same thing over here, and then we'll clear the OSPF process, and that'll cause it to recalculate the link state database. If I could type. And we'll say router ID over here is 10.0.0.2, and then we will say clear. We're just going to do this exact command here. So if we do our shortcuts, let's say copy and paste. Oh, for heaven's sakes. Yes. There we go. Now, the problem is, of course, that we're talking to another neighbor, and this neighbor is going to say, wait a minute, what's going on? And so we'll do the same thing here. Yes, we will. By the way, when you make any changes to OSPF, it's a good idea. If you want them to propagate throughout the network, then this is a good process to go by. All right, let's run our simulation and see what happened here. Now we still have our RIP topology out there. So here is a message going across, and we take a look. There's our router ID, and I know exactly what this particular router ID means. The router didn't pick it, it's not dynamic, so there we have it. And if we keep going, we'll see them going back the other way, and we see we've changed our router ID. Now there's a lot more that we could do with that, but I think that's enough for today. Hopefully you enjoyed this reminder about RIP, a reminder about static routes, and of course our beginning foray into OSPF. Thanks for watching, thanks for listening, and may those packets always reach their destinations no matter what routing protocol you've chosen to use.